All right, so we started section 2.3 last time. Just as a reminder, real quick, of where we were. We had encountered first something called intersection of sets. Intersection of sets is things that sets have in common. And so we see this shaded area below, and it's the part where they overlap. And then we talked about union of sets, and union of sets is like a marriage. You get everything, and so you shade in both the outer parts of sections, in this case A and B, and the part that's inside of the both of them. Okay, so you get sort of the biggest shaded area when you do unions, okay? And we are taking a look now at difference of sets. So the word difference probably brings up into your mind something about subtraction. And not only that, but the symbol that's used for it here also looks like that same symbol. So the difference of sets A and B is written A minus B. It's the set of elements belonging to A and not to B. So the set builder notation for that says the following: A minus B is a set of all X, such that X is an element of A and X is not an element of B. So I have space at the bottom, so I'll draw my picture for this at the bottom as well, like we did on the last two. So we're going to draw the rectangle and the two overlapping circles, and we're going to label them A and B. And for a difference, it means that it is in A and not in B. So where is that in this picture? Or in A, David, what do you think?
I believe you just shade in A, but you wouldn't shade in the middle or B.
Yeah, you're right. So we're going to shade in the piece over here. Kind of looks like a little bit of a moon, right? And we're not going to shade in the overlap, and we're not going to shade in B. Okay, so you're exactly right. That's where we would be shading. So it's right in here, like this. Okay, so this is the part that we're talking about.
Do you know which part of the notes we're at?
Yeah, so we're on differences of sets. It's on the bottom part of section 2.3, the front page. So we're in 2.3 in the front page. All right, I gave a verbal description last time that included my sister-in-law's family, my brother-in-law and sister-in-law's family. So let me kind of draw back into where we were for them, because they have theirs is a really good, that scenario is a really good example for difference of sets, and then we'll do the example. So I mentioned that my brother-in-law and sister-in-law have, between the two of them, 3 children that they are both biological parents for. And then my brother-in-law has a daughter from a previous marriage as well. Okay, so she is the daughter of my brother-in-law biologically, but not my sister-in-law. Everybody remember that example? Okay. So if we were thinking about this scenario, she would be the part out here in circle A. Right? So if circle A were my brother-in-law's biological children, all 4 of his children would be inside this circle. But my niece, her name's Madison, she'd be in the outside part, whereas her 3 siblings, half siblings, would be in the middle, because she has those 3 that share both biological parents. Okay, so that's what we would be including or thinking about as a sort of a verbal example. Now, you'll notice that these sets look similar. They're exactly the same as the ones we did before. So we have our universal set. It's the letters A through G. We've got sets X, Y, and Z. And the directions on this one, number 3, ask us to find X minus Y. Okay, so it means it's included in the first one. It's included in X. So I can't list anything that's not here. Okay, if it's not right there, it's not going to be listed. But if it duplicates with anything in Y, it also does not get included. So what letters duplicate with items that are in Y? A and C. Right? So what elements would be in the difference? Only E and G. Okay, they're elements that are in X, but they are not in Y. So let me make a couple of comments of common mistakes. Probably the most common mistake here that people look at these is that they want to include everything that's still in X and still in Y. But we don't get to include this letter B, because this letter B was not in X to begin with. So don't go throwing extra stuff in, okay? It's just the items that were already in X that did not duplicate to Y. Okay, so our title for this section said set operations. Those are our three set operations, okay? We've got intersection, union, and difference. Yes, sir?
So basically what we're doing is just canceling out the ones that are similar.
Yes, the ones they have in common. Yeah, the ones they have in common get excluded. Only the items that remain from the first set are part of the difference of sets.
So what about C? Because C has C and D. C, will we cancel out C and Z?
Well, this has nothing to do with Z. Like, it's not listed. Our sets have to come from the parts that are listed on the particular problem. So while Z was included in the directions, it's not used on this particular problem. Yeah. Okay, so those are our three set operations. The other part of our title said we were going to do Cartesian products. Okay, so that's the next part that we're looking at. So in order to talk about Cartesian products, we have to talk about what are called ordered pairs. Now, you've seen ordered pairs in algebra before, and it's similar. So an ordered pair is it's in the parentheses, letter A, letter B, right? Where the letter A, the first component comes from one set, and the second component comes from another set. Now, when we do this in algebra, the first letter is representing all our x coordinates, right? It's all the values for x. And the second coordinate represents our y values, right? All of our values in terms of y. So this is actually just a more general form of what you've seen in algebra. In general, AB is not the same as BA. And if you think about an ordered pair, right, in space, that should make sense. If you plotted the point 1, 2, it's not in the same place as if you plotted the point 2, 1, right? Okay, so that follows from that as well. So a Cartesian product, that word product sort of resonates with us as multiplication, and that's the symbol that's used. You see that X multiplication symbol between them. So if we have a set A, and a set B, then the Cartesian product is written A cross B. So, and I usually say cross instead of multiplication, doesn't matter, but it's A cross B. And this is a set of ordered pairs. It's the ordered pairs that take the elements of A from set A and elements B from set B, and it pairs them up. It's just a pairing of things. It's a pairing of things. This is what happens in your youth group when children get together, children, teenagers, whatever, get together and they all pair off. They've got your best buddy, best friend, or whatever, in groups of 3, at least with women, they never work. Can I get an amen? It's true. Groups of 3 are not actually very good. So pairings are much more natural for us. You're seeing in pairs of desks even. Look at this. Right, so pairings are much more natural. We see pairings happening here. So we're going to take a look at the sets U, X, Y, and Z, just like we did before, okay? But we're going to do now the Cartesian product of X cross Y. So as we take a look at this, we're going to create a bunch of ordered pairs. The first thing we have to do is take an element from set set X, and that first one is A. I'm going to pair this element A up with an element from set Y. There's an A over there too. So A would be one pairing. But I could take the value A from here and instead have paired it up with B, right? Sure, could have. Or I could have taken the element A from here and I could have paired him up with C. These are all of the pairings that would include this value A from the first set. And now we go to the next one. Well, what if I used C from the first one? Okay, C. So I use C now, and I pair him up with A. Or I take C and I pair him up with B. Or I take C. Oh, I've got a typo. I'm sorry. That was supposed to say C right there. That one was a typo, sorry. And then I take C and I pair him up with C. But I also need to do this with E in set X. So I'm going to have E paired up with A. E paired up with B. And E paired up with C. And then finally, I'm going to do that with G that's in set X. So I have G with A, G with B, and G with C. And all of this group, in curly braces, would be all the pairings that are possible. So aside from an example like children in a classroom or something like that, this is what happens when you try to arrange pairings of games in athletics as well. Okay, so let me give you a scenario that could make this make sense. Sometimes you don't have a time, like you don't have the ability, if all my letters were different, this would also make this a little bit clearer. But let's say that there's 20 people in your conference and you're not going to play 20 games, right? That's usually the way that would happen. Maybe it's too many for that particular sport. And so they put people in 2 pools. They put 10 of them over here in pool 1, and they put 10 of them in pool 2. And what happens is you either play everybody in your pool, right? That would not be this example. Or maybe you play everyone not in your pool, okay? So you're going to play 10 games, but if you're in pool A, you're only going to play them against everybody over here. Are you tracking with me? Okay, so we have to be able to create, like spaces where you're going to play them. Are you going to play them home or away? Or if this is an intramural situation where you're having a field that's common to both of you somewhere in between, you've got to arrange the fields. You've got to arrange refs. You've got to arrange all the details around that. This is how you would do the pairings of that. Okay, so that's an example of where a Cartesian product would be used. Now, let's count for just a second. How many pairings did we get here? 12. There's 12 of them, right? So if I wanted to count the number of things in this x cross y bit, I would have 12. All right, there's 12 of them. How many did I have in x to start with? Up here at 4. And how many did I have in y? 3. So just thinking with this, how do you get from 4 and 3 to 12? You multiply, right? You multiplied here. And that's exactly what this next slide says. The cardinal number, as in how many are there in this Cartesian product, is found by taking the number of items in one group, the number of items in the other group, and then multiplying them together. Now, there are examples, or there are questions inside of my math lab that just ask you, what's the cardinal number? What is the number of items in the Cartesian product? And then there are questions that ask you, what's the Cartesian product? You're going to have to pay attention to the notation. The key is whether it says an n. N means number of, right? So if it asks you for the number of, then the answer to the question is just going to be a number. That would be my 12 in this example. But if it asks you, what is the Cartesian product, you're going to actually have to write out all those ordered pairs like we did on the previous slide. Pay attention to what the question is asking you. So on this one, right, this is the same question we had from before. We wrote them all out last time. But if this question asked us just to find the number, we do not have to write them all out to do that, right? All we have to do is to actually take a look at the values that we have. We would find the number of items in x, and we would find the number of items in y, and we would multiply them. So like we said, there were 4 items in x. There were 3 elements in y. This is 12. Okay? So don't do more work than you're asked to do. If it asks you to find the number of things, don't go finding all the things and then counting them. That's a little bit overkill, right? We have a simpler way to actually do that counting argument. All right, my last slide of just notes, not problems we're going to work out, takes all of the things that we just did. So this is a really good slide to take a picture of, and it puts them all together. So this is a really good, and it's boxed in on your notes if you haven't printed this, so you know. This boxed in piece is a really good, is a really good place for you to be able to reference back if you're like, what was the difference between them? And you don't have to look at them individually. Yes, Jonathan? Mm-hmm. Got it? Okay. So this is the thing, we already talked about all these. There's one that's on this list that's not in this section because we did it back in section 2.2. That's the complement, this one right here. So if you remember, the complement is all the things that are in the universal set, but they're not in set A. Okay, so that was in a previous set of notes. The rest of these are in this set of notes. We've got the intersection. Remember, this is the things they have in common. We've got the union. The union is when we get where we get everything. We've got the difference, where we get the items in the first, but not the second. Okay, it's in the first set A, not the second set B. And the Cartesian product is a collection of ordered pairs. Okay, so for those of you who are filling in notes, I'm going to pause here and let you write those in. Yeah.
Did you say we regularly use our notes in the exam?
Yep, your notes are all things you can use on your exam. And not just your notes, but anything that you've done work on paper can be brought in. So as you're doing your homework, if you keep organized information as you're working on problems, you can bring that in too. Yep. Okay. All right, are we close? I think we've got a couple still writing. There's several things, two things specifically which should say that we're going to be doing now with Venn diagrams. Okay, so we encountered Venn diagrams last time. Interestingly enough, I teach fifth, sixth graders we call it caravans in our denomination. It's kind of like your Awana program in the Baptist denomination a little bit, kind of like a scouting program. And we're looking at the church, and lo and behold, there's a Venn diagram in their book. And I'm like, look at that. I'm talking about Venn diagrams at school, and Venn diagrams shows up for my fifth and sixth graders at church. Overlaps like that happen a lot in my life. So what we're going to be looking at in the next three problems is going to be looking at something that to me feels a lot like a puzzle, okay? So if you like puzzles, so think about not puzzles like where you like put the puzzle together on the, not cardboard puzzles like that, but mind puzzles. So think about crossword puzzles and Sudoku puzzles, things like that. And you've got apps that do these things too. It feels to me it's like that. So we're going to use Venn diagrams, and I'll show you what I mean. So this one has two sets. It has set A and set B. And so you're going to draw in your Venn diagram a rectangle, and you're going to draw two overlapping circles, just like we've been doing in many of our other sort of pictures to show these spaces, and you're going to label the universal set, okay? How do I know that there's two circles I'm drawing? Well, because there's only two letters listed here. So in a moment, when I move on to number 7, how many circles are going to be? There's going to be 3 because there's 3 letters listed, okay? So this one, 2 circles. Everybody good so far? All right. What you're going to do next is you're going to number the different regions that are in this picture. It doesn't really matter what you number them. You could letter them if you want to, but if you just number them the same way I do right now, then our things will match and it'll be a little bit clearer as we talk together, okay? So I always number mine with 1 here, 2 in the middle, 3 on the right, and 4 on the outside. There are 4 different sort of spaces that these circles and rectangle break this diagram up into. Okay, is everybody good so far? We're just labeling space. All right. The next thing we're going to do is we're going to go to the actual problem that we're given. This problem says A prime union B. Okay? I'm going to write down A prime. And I want you to remember that A prime is a complement notation. It means I want to write down all the numbers that are not in circle A. So what numbers are not in circle A? Okay, so 3 and 4 are not in circle A. 2 is actually still in circle A because it's in the overlapping part, but it's still a part of circle A. Does that make sense to everyone? Cool. The other item in our problem that's listed says B. So this time I don't want the things that are not in B. I actually want the numbers that are in B. So what numbers are in B? Yep, 2 and 3. Okay, everybody good so far? All right, I'm going to draw a line. So I want you to think of this line as like, now I'm going to compare these sets the same way that the problem told me to, and specifically this problem said union. I didn't mean to do that. This is what I want to do. It says union. What does union mean? It means together. It means you get everything. It's the marriage. It's the family picture. I want all of it included. So if I am going to do A complement union B, I include every number that I already listed, but I don't need to duplicate. So I'm going to put them in order. I have 2, 3, and 4, but I don't need to list 3 twice. Does that make sense to everyone? Okay, now this is all the work that supports the answer that we're about to do. Now, some of you are probably about to tell me this was overkill for this problem, and it is. Okay, so some of you could probably look at this and have already told me the answer without what I just did. It's going to be much more difficult to do when there's 3 circles. Okay, so that's why I'm setting it up right now, is so that you can see how it works in a very small case, and then we're going to do it in a bigger case. The question itself wants us to shade the parts of the diagram that fit in with this description. Okay, so we're going to shade the regions of this picture that correspond to the numbers we just listed. So I'm going to shade the region 2, the region 3, and the region 4. And the way that this works in my math lab is it's going to give you kind of like a paint drop bucket kind of thing. And you're just going to click on it and it's going to shade it all in. And I think it shades it in yellow or something like that. Okay, so for the fun of it, we'll just make this a yellow as well. And we'll shade it in yellow. So we're going to shade in region 2. We're going to shade in region 3. And we're going to shade in region 4, which is the outer part of the rectangle out here. This is our answer. Our answer is the shaded regions. Okay? All right, open this one. 2 circles. The next one's more challenging because it's 3 circles. You ready? Okay. So I need a bit bigger of a rectangle because I'm going to have more in it. Hang on. And I need 3 overlapping circles. So this starts to look a little bit like, Olympic rings or something like that as it starts to overlap. I need them labeled A, B, C. I generally label mine, and my math lab stuff will do so as well, as A here, B here, and C. Hang on, I thought I changed that. B here and C down here. Our universal set U is always on the outside. I'm gonna need a little bit more space to work, so let me just shift this over. Okay. All right, so as mentioned before, I need to number the regions. Okay, again, you can number or letter them in whatever way works for you, but again, if we do it all together, our numbers will match for the moment. So the way that I number them is I number it straight across the top. So this would be 1, 2, in the little overlap there, 3. And then I number them through the middle, 4, 5, 6. I number 7 down here for C and 8 on the outside. The 8 on the outside, people will sometimes forget. So this is your reminder right now. Remember, there is an outer region to this. We need to include it in our discussion too. Okay? Now, there are 3 pieces of information up here, right? Just like with algebra, those grouping symbols, those parentheses, tell us where we start. We start inside there. So inside the grouping symbols, we have sets A and B, right? So we're going to write down A, and we're going to write down B, and we're going to list all of the numbers that are in those regions. So what numbers do you see in region A, or circle A? 1, 2, 4, and 5. Everybody okay with that? Great. What numbers do you see in region B? 2, 3, 5, and 6. And you can put them in any order you wish. There's nothing special about our ordering. Okay, if you're a little bit on the OCD side like me, you're probably going to put them in the number order that they go in, right? Go in order. How am I going to join A and B according to the description of the problem I'm given? What they have in common. It's the intersection that they give me the symbol for. Intersection means what they have in common. So as I'm taking a look at my list, I want to only look at the numbers they have in common, which are 2 and 5. And I'm going to write those down. This is 2 and 5. We have now done everything inside the set of parentheses, right? So now we're going to move to the outside of the parentheses, which means that I'm going to include circle C. What numbers are in circle C? 4, 5, 6, and 7. Very good. How am I going to join what's in the parentheses with the C that's outside the parentheses? What symbol does it say? It says union, right? So it's union. We're going to do our A intersect B, and we're going to union that. You like how I turned that into a verb? We're going to union that with C. And what does the union mean? It means I get everything. All right? So I'm going to get the 2. If you wish, I'll do it out of order. I'm going to get the 5. 2 and 5 come from the A intersect B. I also have a 4. I don't need to rewrite 5, so I'm going to skip over it. And then I have a 6, and I have a 7. Okay? But the answer is the shading that I do. So I go back to my picture now. I'm going to shade every numbered region that I still have as part of my answer. So I'm going to shade region 2. And I'm going to shade region 5. And I'm going to shade region 4. And I'm going to shade region 6. And I'm going to shade region 7. And that's my answer. Yeah.
How do we get the 5?
How did we get the 5?
Yeah, like in there.
Well, it's in both lists, right? And union includes everything, including the things where they overlap. Yeah. It's Jeremiah, right? What do you have, Jeremiah?
So for A and B,
Uh-huh.
inside the parentheses, we have the pair. We only shaded the pair version.
Well, we're not shading anything when we just did A and B, right? We were just writing out the numbers. Our shading is always at the very end. So we wait until we get all the numbers at the very end, and those are the pieces that we shade.
And we only take out the ones that are a pair, the exact same.
The ones that match. So on this one we did. But the reason we did that on this one is because the symbol between them was the intersection symbol. If it had been a union symbol, we would have done something different. Now, I will contend that we probably have at least a couple of you in this class who still think that you could have done it without all the numbers on this problem. Okay? And let me just argue what that would look like, because you probably could, some of you, without the numbers. This says I'm supposed to join the circle C, that's everything in circle C, with the part where A and B alone overlap, and that's this piece. This problem you probably could do without the numbers. The reason, for the most part, is because it doesn't have any complements. Yes, ma'am?
On MyMathLab, do we have to draw the circles?
It'll draw the circles in for you. You'll just click on the things where you're shading. It'll show you the overlapping circle pieces, yes. So it's all leading up to this one, where I would argue that for the most part, if you try to do this without the numbers, you're not going to get it right. This one's very messy. It's messy because there's unions and intersections. That's one reason. There's 3 sets. That's a second reason. And some of them have complements, okay? So the primary buildup for all of this is that we can't actually probably reason our way through this very well with this problem like we might have been able to with the last 2. So we're going to start again with our rectangle. Hang on, wrong color. and our 3 overlapping circles. And again, how do I know that there's 3 overlapping circles as opposed to just 2? It lists 3 items in the problem itself, A, B, and C. All right, I'm going to number my regions just like I did before as well. I have 1, 2, 3 across the top, 4, 5, 6 through the middle, 7 down with C, and 8 on the bottom. And again, I start inside the parentheses. The parentheses have A and B complement. A means just what numbers are in A. So what numbers do you see in circle A? Fantastic. 1, 2, 4, and 5. B complement means the things that are not in circle B. So what numbers do you see not inside of circle B? 1, 4, 7, and 8. Don't forget about 8, right? We want to make sure 8's get included there. And what are we supposed to do to join these two together? What symbol does it tell me? Intersection. And what does intersection mean? What they have in common. So what numbers do you see in those two lists they have in common? 1 and 4. Yep. One and 4. Okay, we've done everything in the parentheses now, right? We're going to move on the outside of the parentheses. What set is listed on the outside of the parentheses? C complement. C complement means what? Things that are not in C. So what numbers are not in circle C? 1, 2, 3, and 8. And how does it say we're supposed to join them together on this one? Intersection. So I misspoke before when I said there's unions and intersections on this one. There's only intersections. I apologize. Intersection. What does intersection mean again? What they have in common. So what do you see that these have in common? 1. One little piece only, right? So our A intersect B complement, also then intersecting C complement, is simply the number 1. So where will we shade? Just where circle 1 piece is over here. Does it feel a little bit like a puzzle? I think it kind of does. Now again, you might be looking at this and saying, like, what's the point? Like, I'm shading things. Okay, it's a puzzle, but let's be real. Most of the apps on your phone are puzzles, aren't they? In some fashion. Things are dropping from the sky, you're trying to match things up, whatever. It's a puzzle. So this is a puzzle too. All right.